If someone tells you that the universe is expanding, your mind immediately draws a picture. Maybe you imagine a giant explosion in the darkness, a bright flash, matter flying outward in all directions from a central point. That image feels natural. It feels unavoidable. After all, every expansion we have ever seen has a center. Fireworks explode from a point. A grenade detonates from a location. Ripples in a pond spread outward from where the stone hit. So when we hear that space itself is expanding, we instinctively ask, where is the middle? That question is not foolish. It is deeply human. The problem is that it quietly assumes something that may not be true. We are used to objects moving through space. A ball moves across a room, smoke spreads through air, shrapnel flies through the sky. In every case, space is the background. It just sits there, empty, passive, things move inside it. So when we hear the universe is expanding, we translate it into something familiar. Stuff is flying outward into empty space. But that is not what modern physics describes. The expansion of the universe is not an explosion in space. It is an expansion of space. That sounds subtle, but it is a radical shift. Imagine you are standing in a room and the walls move outward. That is one kind of expansion. Now imagine instead that the ruler you are holding slowly stretches, and every meter becomes longer. Distances increase, but nothing is moving through space in the usual sense. The scale itself is changing. Our brains resist this idea because we evolved in a world where space behaves as a stable stage. We throw things. We chase things. We build structures that assume geometry does not stretch overnight. On human scales, space appears rigid and reliable. It does not swell or shrink between breakfast and dinner. So we internalize the idea that space is fixed. But according to modern cosmology, that intuition breaks down on large scales. Galaxies are not flying outward through some pre-existing emptiness like debris from a bomb. Instead, the distances between galaxies increase because the fabric of space between them stretches. The distinction matters. In an ordinary explosion, there is a center because something specific exploded at a location. The debris travels outward from that location. If you trace all the motion backward, it converges to a point in space. In cosmic expansion, if you trace everything backward, you do not find a single point in today's space where it all happened. You find that everywhere was once compressed. Every region was once denser and hotter. The expansion did not begin at a spot inside the universe. It happened to the universe. Our intuition struggles here because we cannot easily imagine space itself as dynamic. We picture it as emptiness. But in modern physics, emptiness has structure. It can curve. It can stretch. And if space can stretch everywhere at once, then the demand for a central location may not even apply. To loosen our grip on the idea of a center, it helps to build a simpler universe, one we can hold in our hands. Imagine a loaf of raisin bread dough before it goes into the oven. The raisins are scattered throughout the dough. Now imagine that you are not outside looking at the loaf. Imagine you are a tiny creature living on one raisin. You cannot see the entire loaf. You cannot step outside the dough. All you can observe are the other raisins around you. Now the dough begins to rise in the oven. As it expands, something interesting happens. From your point of view, every other raisin begins to move away from you. The ones nearby drift away slowly. The ones farther away separate from you more quickly. If you measure carefully, you would discover a pattern. The more distant a raisin is, the faster it appears to recede. That pattern is not random. It is exactly what astronomers observe when they look at distant galaxies. But here is the crucial question. Are you at the center of the loaf? It feels like you must be. After all, everything is moving away from you. It looks exactly like you are in the middle of some grand expansion. Yet if you could magically jump to another raisin and repeat the experiment, you would see the same thing. From that new raisin's perspective, all the others, including your original raisin, would be moving away. Every raisin sees itself as if it were at the center. And therefore, none of them actually are. The reason is simple once you see it. The raisins are not propelling themselves outward through the dough. The dough itself is expanding. The increasing distances are caused by the stretching of the medium in which the raisins are embedded. This changes the meaning of moving away. The raisins are mostly just being carried along. On small scales, they may jiggle or stick together, but on large scales, the expansion of the dough dominates. No single raisin marks the origin of the process. The expansion happens everywhere at once throughout the dough. Now push the analogy carefully. The loaf of bread does have a center from the perspective of someone outside it. A baker could point to the middle of the dough, but the raisin creatures cannot access that viewpoint. Their entire universe is the dough itself. There is no external coordinate system available to them. In cosmology, we face something even more extreme. The universe is not expanding into a kitchen. There is no oven surrounding it. There is no external observer pointing to a cosmic midpoint. If space itself is all there is, then asking for the center in the usual sense may be like asking a character inside a novel to locate the center of the book in physical space. The raisin bread picture is not perfect. Real galaxies are bound by gravity in complex ways. On small scales, structures resist expansion. But on very large scales, the analogy captures something essential when the fabric itself stretches uniformly. Every observer sees the same recession pattern. And when every location appears central, the idea of a unique center dissolves. Another picture that often helps is the surface of a balloon. Imagine a balloon before it is inflated. Take a marker and draw small dots all over its surface. These dots represent galaxies. Now begin to inflate the balloon slowly. As the rubber stretches, every dot moves away from every other dot. If you were a tiny two-dimensional creature confined to the surface, you would notice something remarkable. No matter which dot you lived on, you would observe all the others receding from you. The farther a dot is from you, the faster it appears to move away as the balloon expands. This is not because your dot sits at the center of the surface. In fact, there is no center on the surface itself. The center of the balloon exists only in the three-dimensional space outside the surface. But the surface creature has no access to that external dimension. For that creature, only the surface exists. Within that surface, there is no privileged point. This analogy captures something important about our universe. On very large scales, space behaves as though it is stretching uniformly, much like the rubber of the balloon. Every region sees every other distant region moving away. There is no special location where the expansion began, at least not within the space we inhabit. However, the balloon analogy must be handled carefully. When we inflate a balloon, it expands into the surrounding air. There is an outside environment into which the balloon grows. It is natural, then, to ask what the universe is expanding into. But this question assumes that the universe is like the balloon embedded in something larger. According to our best physical theories, that assumption may be unnecessary. The expansion of the universe does not require an external space. The balloon's surface is meant to represent all of space in two dimensions. Its growth illustrates how distances can increase without needing a center within the surface itself. The extra dimension in the analogy is a visual aid for us, not necessarily a physical feature of reality. In our universe, space is not stretching into pre-existing emptiness. The metric that defines distances between points changes with time. Galaxies are not flying outward into a void beyond the cosmos. Rather, the amount of space between gravitationally unbound systems increases. The geometry evolves. What makes this difficult to grasp is that we are used to thinking of space as a container. We imagine it as an empty box that holds matter. The balloon analogy forces us to consider a different view. Space is not merely a container, but something with geometric properties that can change. If you are confined to the surface, you can travel in any direction and never encounter an edge. You might circle the balloon and return to your starting point. The surface is finite in area, yet it has no boundary. This challenges another deep intuition. We often equate finite with having an edge, but geometry allows more subtle possibilities. Whether our universe is exactly like the balloon's surface is still an open question. Observations suggest it is very close to flat on large scales, but flat space can also expand without possessing a center. The crucial lesson remains when geometry itself evolves uniformly. The concept of a central point within that geometry may simply not exist. For most of human history, space was treated as a silent background. It was the stage on which events unfolded, but it did not participate in the drama. Planets moved, light traveled, objects fell. Space itself just sat there, empty and unmoving. This view was deeply embedded in classical physics, especially in the framework developed by Isaac Newton. In that picture, space was absolute. It existed independently of matter and time like a vast, rigid grid extending forever in all directions. Then in 1915, Albert Einstein changed that picture completely with his theory of general relativity. In this new framework, space was no longer passive. It became dynamic. It could bend, stretch, and curve in response to matter and energy. Gravity was no longer a force pulling objects through space. Instead, massive objects changed the geometry of space-time itself, and other objects followed the curved paths created by that geometry. This was not just a minor correction. It was a conceptual revolution. If space can curve near a star, then space is not a rigid container. It has structure, it has properties. It can evolve. Einstein initially believed the universe as a whole was static. Like most scientists of his time, he assumed that on the larger scales, the cosmos neither expanded nor contracted. However, when he applied his own equations to the universe as a whole, he found something unsettling. The mathematics did not naturally describe a static universe. Instead, the equations suggested that space should either expand or collapse under gravity. To force a static solution, Einstein introduced an additional term into his equations called the cosmological constant. It was a mathematical adjustment designed to hold the universe steady. But the equations left to themselves resisted stillness. Soon after, in 1922, Alexander Friedmann explored Einstein's equations without imposing the requirement of a static cosmos. He found solutions that described a universe whose scale changes with time. Depending on the density of matter and the properties of space-time, the universe could expand or contract. The equations did not require a central explosion. They described a changing geometry everywhere at once. This was a profound shift. Expansion did not mean matter flying outward from a location inside space. It meant that the metric defining distances between points in space was evolving. If you imagine marking coordinates on a flexible grid and then stretching the grid itself, the distances between fixed coordinate points increase even if those points are not moving in the ordinary sense. In general relativity, the universe can be homogeneous and isotropic on large scales, meaning it looks statistically the same in every direction and from every location. When the geometry of such a universe changes uniformly, every observer sees distant galaxies receding. No observer occupies a special place. The absence of a center is not an added assumption. It falls naturally out of the mathematics when space is treated as dynamic. Once space becomes something that can evolve, the need for a fixed background or central reference point dissolves. The universe does not expand from somewhere. Its geometry changes everywhere. The idea that the universe is expanding did not begin as philosophy. It began as measurement. For centuries, astronomers debated whether the faint spiral shapes in the night sky were part of our own Milky Way or distant. Island universes, far beyond it. The scale of the cosmos itself was uncertain. In the 1920s, Edwin Hubble carefully measured the distances to several of these spiral nebulae and showed that they were far outside our galaxy. They were not small clouds within the Milky Way. They were entire galaxies of their own. The universe suddenly became vastly larger than previously imagined. But Hubble's most important discovery came next. By studying the light from distant galaxies, he noticed that their spectral lines were shifted toward the red end of the spectrum. This redshift indicated that the light waves had been stretched. The simplest interpretation was that these galaxies were moving away from us. Even more striking was the pattern. The farther away a galaxy was, the greater its redshift. In other words, more distant galaxies appeared to be receding faster. This relationship became known as Hubble's law. At first glance, this might seem to confirm the idea that we sit at the center of a cosmic explosion. After all, if everything is moving away from us, doesn't that make us special? But the key insight is symmetry. If the expansion of space is uniform, then observers in any galaxy would see the same pattern. Imagine again the raisin bread or the balloon surface. From any raisin, all others recede. From any dot, all other dots move away. The observation of universal recession does not single out a center. It reflects a global change in scale. The redshift we measure is not primarily due to galaxies racing through space like bullets. On large scales, it is better understood as the stretching of space itself. As light travels across the universe, the space through which it moves expands. The wavelength of the light stretches along with it, shifting toward red. This distinction matters. If galaxies were simply flying outward from a central point through static space, we could, in principle, trace their motion back to a specific location. But when the expansion is encoded in the geometry of space-time, there is no single point inside the universe that serves as the origin. Observations of the cosmic microwave background radiation strengthen this picture. This faint glow, left over from an early hot phase of the universe, is remarkably uniform in all directions. Its uniformity suggests that, on large scales, the universe has no preferred direction and no preferred location. The data do not show signs of us being near a central explosion site. Instead, they are consistent with a universe in which space itself expands uniformly everywhere. The evidence does not point to a center hidden somewhere beyond our telescopes. It suggests that the concept of a center may not apply at all. Modern cosmology rests on a deceptively simple assumption called the cosmological principle. It states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means that averaged over vast distances, matter is distributed uniformly. Isotropic means that the universe looks the same in every direction. These are not statements about local details. Galaxies cluster stars form. Voids exist. But when you zoom out far enough, hundreds of millions of light years, the irregularities smooth out. Why make such an assumption? Because observations support it. Large galaxy surveys reveal a cosmic web of filaments and voids. Yet when averaged over enormous volumes, the density becomes statistically uniform. The cosmic microwave background radiation, the afterglow of an early hot state, appears nearly identical in every direction, with only tiny fluctuations. Those fluctuations are crucial for structure formation, but their small size reinforces the larger pattern of uniformity. If the universe is homogeneous and isotropic, something powerful follows. There can be no preferred location. If one region were fundamentally special, if there were a true center, then the large-scale structure would look different depending on where you stood. Observers near the center would measure different expansion patterns than observers far away from it. But when we model such universes mathematically, the symmetry breaks. The data do not support that asymmetry. Consider what a genuine center would imply. Imagine space expanding outward from a specific point. Observers closer to that point would see galaxies distributed differently than observers farther away. The cosmic microwave background would show directional distortions. The redshift distance relationship would vary depending on location. Yet our measurements show remarkable consistency. Wherever we look on large scales, the expansion behaves the same way. This uniformity is not trivial. It is the reason the equations of general relativity admit simple cosmological solutions known as Friedmann, Lamactre, Robertson, Walker models. In these models, the scale factor, a function that describes how distances change with time, applies everywhere. Space expands or contracts uniformly, without singling out a central coordinate. It is important to understand that no preferred location does not mean nothing is happening. Expansion is very real. Distances between gravitationally unbound galaxies increase. Light from distant objects is stretched. But the change occurs in a way that treats every large-scale region equally. There is also a deeper lesson about symmetry. In physics, symmetries often guide us toward truth. When laws appear the same regardless of position or direction, it suggests something fundamental. The absence of a center is not a philosophical preference. It is a reflection of symmetry in the data and in the governing equations. If every observer sees the same large-scale behavior, then the universe does not revolve around a hidden middle. The expansion is not radiating from a cosmic throne. It is encoded in the structure of space-time itself, unfolding uniformly across the vastness of reality. The phrase Big Bang is one of the most misleading names in science. It suggests noise, fire, and a violent explosion that blasted matter outward into empty space. That image is so powerful that it shapes how people imagine the beginning of the universe. But the term does not accurately describe what our equations and observations imply. When physicists speak about the early universe, they are not describing an explosion at a point inside space. They are describing a state in which the entire observable universe was once extremely hot and dense. The key word is entire. Every region of space was compressed. Every location was closer to every other location. If you run the cosmic expansion backward using the equations of general relativity, the distances between galaxies shrink. The temperature rises. The density increases. Eventually, you approach a limit where known physics breaks down. But notice what does not happen in this description. You do not arrive at a particular spot in today's universe where the explosion occurred. There is no coordinate you can point to and say, that is where it began. Instead, you find that all of space was once in a different condition. The Big Bang was not an event in space. It was an event of space. To see why this matters, imagine again the balloon surface. If the balloon is deflating backward in time, every dot moves closer to every other dot. In the limit, the surface shrinks, but no dot becomes the central origin of the shrinking. The entire surface contracts uniformly. The beginning is not located at a special position on the surface. It is a global state. Similarly, when cosmologists say the universe began in a hot, dense state about 8 billion years ago, they mean that the scale factor of the universe was much smaller. Distances between points were compressed everywhere. The laws governing matter and radiation operated under extreme conditions. But there was no pre-existing emptiness waiting to be filled by an explosion. The misunderstanding often arises from the way we experience explosions in daily life. A bomb explodes in a room. The fragments fly outward into surrounding space. There is a clear center. But that scenario assumes a background space that already exists. In cosmology, the background itself evolves. There is no external room. It is also important to acknowledge the limits of this picture. When we extrapolate back to extremely early times, we reach what is called a singularity in classical general relativity, a point where density and curvature become infinite. Most physicists believe this indicates that the classical theory is incomplete under such conditions. A quantum theory of gravity would be required to describe what truly happened at the earliest moments. So even the phrase, the beginning, must be used carefully. We understand the universe well from a tiny fraction of a second after this hot dense phase began. Before that, our knowledge becomes uncertain. What remains clear, however, is that the Big Bang does not imply a central location in space. It describes a transformation in the state of the entire cosmos, not an explosion from a cosmic center. To go deeper, it helps to step away from 3 dimensions entirely and imagine a simpler world. Picture a universe with only 2 dimensions, like a perfectly thin sheet. Creatures live on this sheet. They can move forward and backward, left and right, but they have no concept of up or down. Their entire reality is confined to the surface. Now imagine that this sheet stretches over time. The distances between all points increase uniformly. If 2 of these 2-dimensional creatures measure the distance between their homes, they find it growing. If they look at distant cities, they observe them slowly receding. The farther away a city is, the faster it seems to move away. From their perspective, their universe is expanding. Naturally, they might ask the same question we ask, where is the center? If everything is moving apart, there must be a middle point from which it all began. But if the sheet stretches uniformly everywhere, there is no special point within the sheet itself. Every location experiences the same increase in distances. If one creature claims to live at the center, because all others are moving away, another creature in a distant region can make the exact same claim with equal justification. The symmetry undermines the idea of a unique center. Now consider another variation. Suppose this two-dimensional universe is not an infinite flat sheet, but the surface of a sphere. The creatures can travel in any direction, and if they journey long enough, eventually return to where they started. Their world is finite in area, yet it has no edge. There is no boundary where space ends. If that spherical surface expands, like the surface of an inflating balloon, the distances between all points increase. Yet there is still no center within the surface. The center of the sphere exists in a higher dimension, but the two-dimensional inhabitants have no access to it. For them, only the surface is real. This thought experiment exposes how strongly we rely on embedded perspectives. We instinctively imagine our universe as something sitting inside a larger container. But if space itself is all there is, then asking for a center within it may be misguided. Observations suggest that our universe is very close to spatially flat on large scales. Flatness does not automatically imply infinity, but it allows the possibility. An infinite flat universe that expands uniformly would have no center, because infinity has no middle. You cannot choose a central point in an endless grid without arbitrarily privileging it. Even if the universe is finite but unbounded, like the surface of a sphere in higher dimensions, it still would not contain a center within its own geometry. The concept of a center depends on the embedding space, which may not physically exist. The deeper lesson is that geometry does not require a central anchor. A space can be curved or flat, finite or infinite, expanding or contracting without containing a privileged location. When expansion is a property of the geometry itself, the demand for a central point may simply reflect the limitations of our everyday spatial intuition rather than a feature of reality. By now, it is clear that space is expanding, and that this expansion is not happening from a central point. But there is more we know, and more that remains mysterious. Observations over the past century have allowed us to measure the rate at which the universe expands, described by the Hubble constant. Using telescopes and sophisticated instruments, astronomers can determine the speed at which distant galaxies recede and their distance from us. This relationship provides a quantitative understanding of expansion and confirms that it is uniform on very large scales. Beyond simply measuring expansion, we know that the farther away a galaxy is, the faster it moves away. This pattern is observed consistently across all directions, reinforcing the idea that there is no preferred location. The universe behaves as if every point is equally ordinary in its experience of expansion. Galaxies themselves are not moving through space like ships on an ocean. Rather, the space between them stretches. On small scales, gravity binds stars into galaxies and galaxies into clusters, counteracting expansion. But beyond these scales, expansion dominates, and distances increase steadily over time. We also know that the universe was once in an extremely hot and dense state. Light from that early era, known as the cosmic microwave background, permeates the universe and provides a snapshot of the cosmos approximately 380,000 years after the Big Bang. The uniformity of this radiation, with only tiny fluctuations, suggests that the universe was remarkably similar in all directions, even at very early times. This reinforces the idea of a centerless expansion. The early universe was not an explosion radiating outward from a point. It was a global state present everywhere. The expansion of space is accelerating. Observations of distant supernovae and large scale structures show that galaxies are not just receding. The rate at which they move apart is increasing. This phenomenon is attributed to what physicists call dark energy, a mysterious component of the cosmos that counteracts gravitational attraction on large scales. Despite decades of study, the nature of dark energy remains unknown. It is a label for an observed effect, not an explanation. We can measure its impact, but we do not yet understand why it exists or what drives it. There are other unknowns. We do not know whether the universe is infinite or just enormously large. We do not know what, if anything, came before the hot, dense state that marked the beginning of observable expansion. We do not yet understand why the laws of physics allow space to expand in this way. The framework of general relativity describes the evolution of space, but the deeper reason for its initial conditions and for the acceleration remains elusive. Human beings struggle with these concepts because our intuitions are tuned for life on Earth. We evolved to navigate surfaces, throw objects, and anticipate motion within a rigid spatial environment. Our minds expect a center for any expanding system and a background into which things move. Cosmic expansion violates both assumptions. It is not an object moving through space, it is space itself changing. Grappling with this requires abstract thinking, mathematical reasoning, and acceptance that our sensory intuition is inadequate for cosmic scales. Yet, despite these limits, we can measure, model, and describe the expansion accurately. We know what happens on large scales. We know the universe has no center. We know space itself stretches, carrying galaxies along. And we know that each observation, no matter where it is made, reflects the same underlying pattern. This understanding represents one of humanity's most remarkable achievements, a precise knowledge of the structure and evolution of a cosmos, in which every location is equally ordinary, yet every moment reveals profound truths about the nature of reality. Even with everything we have learned about the universe, there remain profound mysteries that challenge our understanding. While we can measure the expansion of space, map the distribution of galaxies, and detect the faint glow of the cosmic microwave background, we do not know why the universe exists in the first place. We do not know the ultimate origin of the laws of physics that govern expansion, or the fundamental nature of the vacuum that allows space itself to stretch. We have names for some of the phenomena we observe, such as dark energy, but these are placeholders for ignorance, labels that describe effects without explaining causes. One of the most unsettling aspects of cosmic expansion is that the very concept of a center may be meaningless. In our daily lives, every expansion we observe has a starting point, a central location from which things move outward. A firework explodes, smoke disperses, ripples propagate from a dropped stone. In all these cases, the geometry of space is static, and motion occurs within it. When space itself expands, these assumptions break down. Distances grow everywhere, simultaneously, without an origin point embedded within space. Asking where the center is may be like asking what is north of the North Pole, a category mistake, a question that does not apply to the system we are trying to understand. Humans struggle with these ideas because our brains evolved to handle problems on scales very different from the cosmos. We are equipped to throw rocks, track predators, navigate terrain, and recognize patterns in local space. These skills helped our ancestors survive, but they are ill-suited for thinking about curved, dynamic space-time, or for imagining a universe in which every point experiences expansion equally. Our intuition insists on centers, edges, and fixed backgrounds, even when none exist. The universe does not conform to our instincts. Despite these limitations, we have developed tools to see beyond intuition. Mathematics allows us to describe the evolution of space-time, to predict how light from distant galaxies will stretch, and to calculate how the universe behaves billions of years into the future. Observations confirm these predictions with astonishing accuracy. The symmetry we observe, homogeneity and isotropy, tells us that every region is equivalent on cosmic scales. Expansion is uniform. No observer occupies a privileged position. No central point exists where the universe began in space. The Big Bang was not an explosion in a pre-existing container. It was a global condition in which space itself had a smaller scale and higher density. This realization reshapes how we understand our place in reality. We are not at the center of creation. There is no cosmic throne, no preferred vantage point, no ultimate location from which events radiate. Every point in the universe is equally ordinary, and yet, within that ordinary framework, remarkable phenomena occur. Galaxies form. Stars ignite. conscious beings emerge capable of observing, questioning, and comprehending aspects of this centerless cosmos. Our existence is both insignificant in terms of location and extraordinary in terms of awareness. The absence of a center forces us to confront a philosophical but scientific truth. The universe unfolds without reference to a privileged point. Its expansion, its geometry, and its laws are impartial. Understanding this requires humility, rigor, and a willingness to abandon intuitive assumptions. Yet it also reveals a profound beauty. The cosmos is not designed around us, but we have the capacity to understand it. In a universe without a center, every observer is simultaneously ordinary and uniquely capable of grasping the extraordinary. Reality, unbound and uniform, continues to expand, and within it, thought itself has emerged to reflect on the cosmos, on space, and on the infinite possibilities of existence.